Imagine staring at a math problem that looks like, well, pure chaos. A polynomial equation with an x to the power of 8, filled with these really complex, messy coefficients. It feels impossible to solve, right? Intimidating is probably an understatement.
Absolutely. High degree polynomials, especially ones with intricate coefficients like we're seeing in our source material today, they can look like just impenetrable walls of numbers and symbols. Where do you even begin to find the x values that make the whole thing true?
That's exactly what this deep dive is all about. We're diving into a set of mathematical notes and formulas that, well, they present a specific, pretty powerful method for tackling these beastly equations. We're focusing specifically on degree 8 polynomials today and how to find their roots.
Yeah. Our sources detail an approach that transforms these complex problems, revealing some surprising structure and, frankly, some remarkably clean solutions hidden within all that dense notation.
So, our mission today is to be your guides through these notes, sort of unpack the step by step method, understand the key tools they're using, and see how they actually arrive at the roots for these complicated equations. It's really about finding the elegance within the complexity.
Right. Let's jump right into the first polynomial presented in the notes. It's a classic example of what we're up against here.
Okay. It starts innocuously enough with XA, but then you look at the coefficients. For the XA term, it's minus 16. Simple enough. But then the XA term has 732 divided by 8 squared.
Mhm.
And the rest follow a similar pattern, large numbers over powers of 8. The source material labels these initial coefficients using a notation called LRUQ,
Oh, yes, the LRQ.
where R tells you which coefficient you're looking at, starting from RU0 for that XA term's coefficient up to R7 for the constant term. So the coefficient for XA is L0Q, XXA is 16. The coefficient for XA is L1Q, is L01Q is 71328D, and so on. It's quite a mouthful of a polynomial.
It really is. And the method outlined in these notes, it centers around calculating a new set of values called SRQ directly from these initial LRQ coefficients. This is the core transformation step, really.
Okay, and the key tool the source mentions again and again for this calculation is something called the discriminant formula of Mourad Sultan Ezouidi Hism. What does that formula actually do for us here?
Well, think of this discriminant formula as a kind of sophisticated processor. It takes the original coefficients, those LRQ values we just mentioned, and it mathematically manipulates them in a very specific way to generate these new SRQ values. And these SRQ values, they aren't just random numbers, they capture different structural properties of the polynomial, things related to its roots. The calculation itself is complex, it's all laid out in the notes, but its purpose is to give us the numbers that will form a new and hopefully much simpler equation.
Got it. Okay, so the source applies this formula to our first polynomial's LRQ coefficients to get these ARQ values. And here's where we start to see the method's power, right? The source shows the calculated results for RSU for this specific polynomial. And it turns out that S0R, S2R, SR4, and S6R, they're all zero.
Exactly. All the even indexed ones are zero. And the odd index error values are specific integers. S1R equals 446, S5R equals 2196, and S7R equals 3465.
This is where the transformation happens. The source explains that these calculated SRQ values become the coefficients of a new polynomial. Specifically, the value SKR becomes the coefficient for the SAK term in this new equation.
Which means
So because S2R, 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 and S6R is zero, all the terms with odd powers of x just vanish.
right, they just disappear,
Right.
which leads to a dramatically simplified polynomial, one involving only even powers of xx era plus 496xr plus 3465 equals 0. Just look at that side by side with the original one we started with. It's so much cleaner.
It really is. And the next move shown in the source is what you called it elegance earlier, and it kind of is letting x pawn x fun.
Because the simplified polynomial only has those even powers of x. Substituting x for xon transforms it into a polynomial in terms of x. Since x is just x real, x1, so on, we get a much more manageable degree 4 polynomial in x. That's xo, 36x, plus 446x, plus 365 equals 0. So we've gone from a pretty messy degree, 8 eigenexons, down to a relatively clean degree, 4 in x.
And the source material reveals the absolutely surprising result for the roots of this quartic equation in x. This is that critical intermediate step as it shows the power of the method. The roots aren't complicated decimals or messy radicals. They're simply the integers 3, 7, 11, and 15.
This is the core insight, yes. The method, by applying the discriminant formula and transforming the polynomial, it leads us to a point where the crucial intermediate solutions are just simple integers. It sort of extracts that fundamental simplicity from the original complexity. That's the real win here, I think.
Right. Okay, so now to get back to the roots of the original ECEC polynomial, We just need to reverse that substitution. Since x equals x sexton, the roots of the original equation must be the square roots of these x values.
Which gives us 3, 7, 11, and 15. And that's the set of 8 roots shown in the source for the first polynomial.
But then the source also presents a second way of expressing these same 8 roots, using something called x notation. And these expressions, interestingly, incorporate the original polynomial's S0Q value, which, if you remember, was made as 16.
Yes, that's right. The notes show these roots can also be expressed as 16 down near 3, 8, 16 down near 7, 8, and 16 down near 16, 8. Notice how the square roots of those x values, the 3, 7, 11, 15, reappear here, but now they're combined with that initial x0q coefficient, well, minus L0q, so plus 16 divided by 8.
Yeah.
The source confirms both sets of expressions represent the identical 8 roots of the original high-degree polynomial. Two ways of looking at the same result.
Okay, fascinating. Let's move on then to the second degree 8 polynomial tackled in the source material. It has a different set of coefficients, also presented as LRQ values. For instance, its L0Q is 1 this time, and its L7Q, that's the coefficient of the constant term, is 0.
Right, different starting point. And the notes show the same powerful process being applied again. They take these new LRQ values and they use that same discriminant formula we mentioned, Mourad, Sultan, Ezouidi, HSM's formula, to calculate a new set of SRQ values for this specific polynomial.
Okay, following the steps. The source again reveals that for this second polynomial, the even indexed SR values, S0R, S2R, S4R, S6R, guess what? All 0 again.
All 0 again, consistent pattern there. While the odd index values this time are S1R equals 10, S3R equals 35, S5R equals 2050, and S7R equals 24. Different numbers, but the same odd index pattern.
And using these SRQ values as the coefficients for the terms by 8k, just like before, leads to another simplified polynomial with only even powers of x, xeo, 10 by r plus 35 before bas plus 24, it equals 0.
Looks familiar in structure, doesn't it? And when we apply that same substitution, x equal xx it turns into a degree 4 polynomial in x. xaa plus 35x powers plus 50x plus 24 equals 0.
And the roots found in the source for this second quartic equation in x, you might guess, once again, simple integers. 1, 2, 3.
Yeah. This really reinforces the core insight, doesn't it? The method consistently leads to these remarkably clean integer roots at this intermediate degree 4 stage. It seems it works regardless of the specific complex coefficients of the original degree 8 polynomial, at least as long as they fit the kind of structure this method is designed for.
Okay, so deriving the roots of the original x's polynomial from these x values is pretty straightforward again. X.
That gives us owns 1, which is just own 1, 6 Jizo 2, 3, and 4, which is MCO. So listing them out gives us the 8 roots for the second polynomial, septem set 2 is SSE.
And just like the first example, the source provides that alternative expression for these roots using the x notation, this time involving the second polynomial's L0Q value, which was 1.
These roots are given as 1 on the 1 8, 1 on the 2 8, and 1 on the 3 8. You can see how these map back to the square roots of the x values 1, 2, 2, 3, combined with that initial L0Q of 1, all divided by 8. And if you work them out, like 1 plus 1, 8 is 28 or 14, 1, 1, 8 is 08, which is just 0, then 1 plus 2, 8 is 38, 1, 2, 8 is nearing 18, and you have the ones with the square roots too. They are the same 8 roots, just expressed differently using that initial coefficient.
Interesting. The source material we looked at also it briefly touches on how variations of this method can be applied to related polynomials, like a specific degree 7-1 derived from the second example, noting that the approach is similar, but the root formula has changed slightly.
Yeah, it suggests the broader potential of this transformational technique, even if the exact outcome or the form of the roots changes depending on the polynomial's specific structure and degree, it's not just a one-trick pony for these exact degree 8s.
So let's just recap our journey through these notes quickly. We started with polynomial equations that looked incredibly complex, frankly, filled with daunting coefficients.
Yep. And we saw how the source material presented a specific structured mathematical method. It involved taking those initial coefficients, the LRQ ones, applying a powerful discriminant formula to calculate a new set of values, the SRQS.
And using those SRQ values as coefficients to form a new polynomial, one that, thanks to that pattern of calculated values where the even ones were 0, simplified dramatically to include only even powers of x.
Then the crucial step was the substitution x equals xert, turning the problem into a degree 4 polynomial in x. And the remarkable insight, really the core success of this method, as shown in the sources, is how the roots of these intermediate quartic equations consistently turned out to be surprisingly simple, clean integers, like 3, 7, 11, 15 in the first case, and 1, 2, 3, 4 in the second.
Yeah, quite something. Ultimately, this method led directly to finding the elegant sets of roots for the original complex degree 8 polynomials. It really shows that even when a problem looks impenetrable, the right structured approach and specific mathematical tools can reveal underlying simplicity and lead to clear, understandable results.
Absolutely. And the source material leaves us with a final kind of thought provoking point. For both of those degree 8 polynomials, they provided two distinct ways of writing the final roots. There was the more intuitive sex form,
Mhm.
derived directly from the quartic roots,
Right.
and then there was that egg formula that ties the roots back to the original polynomials L0Q coefficient. Remember, the 16 0Q and the 1128 forms.
So this raises a fascinating question for you, the listener, to consider. How do these different expressions for the very same set of roots mathematically relate to each other? And maybe more deeply, what structural properties of the original polynomial do these two forms reveal?
Mm.
Especially that second form, the one involving L0Q. What does it tell us about the polynomial's relationship to its initial setup? That's definitely something you can keep mulling over. With daunting coefficients.
Yep. And we saw how the source material presented a specific structured mathematical method. It involved taking those initial coefficients, the LRQ ones, applying a powerful discriminant formula to calculate a new set of values, the SRQS.
And using those SRQ values as coefficients to form a new polynomial,
Hmm.
one that, thanks to that pattern of calculated values where the even ones were zero, simplified dramatically to include only even powers of x.
Then the crucial step was the substitution x equals xert, turning the problem into a degree 4 polynomial in x. And the remarkable insight, really the core success of this method, as shown in the sources, is how the roots of these intermediate quartic equations consistently turned out to be surprisingly simple, clean integers, like 3, 7, 11, 15 in the first case, and 1, 2, 3, 4 in the second.
Yeah, quite something. Ultimately, this method led directly to finding the elegant sets of roots for the original complex degree 8 polynomials. It really shows that even when a problem looks impenetrable, the right structured approach and specific mathematical tools can reveal underlying simplicity and lead to clear, understandable results.
Absolutely. And the source material leaves us with a final kind of thought provoking point. For both of those degree 8 polynomials, they provided two distinct ways of writing the final roots. There was the more intuitive sex form,
Mhm.
derived directly from the quartic roots,
Right.
and then there was that egg formula that ties the roots back to the original polynomials L0Q coefficient. Remember, the 16 0Q and the 1128 forms.
So this raises a fascinating question for you, the listener, to consider. How do these different expressions for the very same set of roots mathematically relate to each other? And maybe more deeply, what structural properties of the original polynomial do these two forms reveal?
Mm.
Especially that second form, the one involving L0Q. What does it tell us about the polynomial's relationship to its initial setup? That's definitely something you can keep mulling over.